Hello everyone, I am Aruna Gundeti. Now we are going to discuss about our project called Advancing Computational Techniques Evaluating Runge Methods for Real World Applications. And these are our teammates. Let's talk about the project. This project provides an overview of Runge methods which are widely used for solving ordinary differential equations, which is called ODEs, and it introduces various Rangekute methods briefly in the next slides. Let's talk about the contents. These are the contents or the topics which we are going to cover in this presentation. Now let's talk about overview of the project. The Ranjekutte method is a widely used numerical approach to solve initial value problems, and it also called IVPs for ordinary differential equations. It provides an iterative way to approximate the solutions of differential equations by step, and these derivatives are used to predict the behavior of the function. An IVP is type of differential equation where initial conditions are provided, and these conditions are used to specify the value of unknown function in its particular domain. Let's talk about one of the method of Runge-Kutta method, that is Euler's method. And Euler's method is the basic foundation of Runge-Kutta methods. It is classified as first order method. It means it evaluates the solution using a single derivative at each step. Let's talk about some key features. It is very easy to implement and it is less accurate for large significant errors, and it is very difficult for large size equations. And there are some steps for Euler method. And the first step is using starting with initial condition, that is y dash of t naught and initial value of y of t naught. Next step is choosing the step size h, where h defines the interval over which the approximation proceeds. And next, then iterate to the approximate solution at each step n, where n is the step number, tn equal to t naught plus nh. We had a formula for Euler's method. For the for the derivative function f of t of n comma yn, to compute the slope at current point tn comma yn, we need to predicate the value of the solution at the following step, and the function is yn plus h into f of tn comma yn equal to yn plus 1, where yn is current value of the solution, h is step size, tn is current time, and the function f of tn comma yn is derivative function at the point tn comma yn. And next, update the solution yn to yn plus 1 for the next iteration. And the next method of Range-Kutta method will be continued by the Navya.
So we are going to discuss the midpoint method. It is also known as the second order RK method, meaning its global error is proportional to h square. So its core idea is that it improves upon Euler's method by estimating the slope not only at the beginning of the interval but also at the midpoint. So it gives a more accurate prediction for the next value. So it is naturally more precise than Euler's method, but it is less precise than higher order methods. Going to the calculations, here we have two slopes. K1 is the initial slope, which is calculated at the beginning of the interval, and K2 is the midpoint slope, which is calculated at the midpoint h by 2 and using the estimate from K1. And the last is the update step, yn plus 1, which is calculated using the yn and the K2 estimate. The key takeaways from RK2 or midpoint method are it involves two evaluations of the derivative function per each step, and also it balances the simplicity and accuracy for moderate applications. And then the next method is the RK3 method. It is also known as the Ralston's method, and it is third order, meaning its global error is proportional to R cube. Although it is more accurate than RK2 or midpoint method, it is less so when compared to the higher order methods like RK4, and it involves three evaluations of the derivative functions at each step. So its core idea is that we are going to combine three slopes K1, K2, K3, and then we are going to take the weighted average for getting more higher precisions. These are the steps. K1 is the initial slope starting it is calculated at the beginning of the interval, and K2 is the midpoint slope which is calculated at the midpoint h by 2 and K1 estimate. K3 is the final slope. And as you can see, the update step has been modified by using the weighted averages of K1, K2, and K3. Going forward, these are the notions that we are going to use. Yn is the approximate value of the solution at time tn, and h is the step size. F of ty is nothing but derivative function. K1, K2, and K3 are the slopes. Going forward to the RK4 method, it builds upon the RK3 method by calculating uh, another slope K4. It is fourth order method, meaning its local error is proportional to h bar 4, and it is one of the most accurate and widely used methods in the practice. These are the steps that we are going to calculate. K1 is the initial slope, K2 is midpoint slope, K3 is nothing but revised midpoint slope, and then the final slope K4. Here it is added step for the RK3 method, and then yn plus 1 is calculated using those weighted averages. The key takeaways that we can get from RK4 is that it involves 4 evaluations of the derivative function, and it also provides an excellent trade-off between the computational cost and accuracy. And it is often the most default choice in applications because of its reliability and also its higher precision compared to lower order methods. Pranay will continue from here.
So coming to the applications, we have three main applications here. First one, RK method is used for simulating planetary orbits and spacecraft trajectories. Runge Kutta method help account for complex gravitational forces. It is also used for modeling reaction rates in combustion engines or chemical reactors. It uses systems of ODEs to predict how concentrations change over time. It's used in tracking species growth, predator-prey interactions, or disease spread. RK methods simulate ecological systems for better resource management. Let's look at some hypothetical scenarios. Here, our main goal is for modeling fish population growth. Coming to the problem statement here, we want to model the growth of a certain fish species in a lake using a simple differential equation dy by dx is equal to x plus y, where y represents the population of the fish, x represents the time. And here we took initial values of x naught and y naught as 0 and 1. Uh, Coming to the second scenario for the application of RK2, the the Rangakutta method allows precise modeling of fish population growth considering changes in environmental conditions and other external factors. Let's look at the second hypothetical scenario. In this scenario, we can map the components of the differential equation to RK4 script where it has four models as discussed in the earlier slides, where initial slope method and the remaining three methods. Let's look at the code for the Euler method. Let's look at the code for the Euler method where it uses a single slope estimate to calculate the next point. Yi plus 1 is equal to yi plus h into f of xi yi. This code initializes x and y, computes the next point iteratively, and plots the solution. Here we can see x values of 1 is equal to x naught and y values. These are set for the initial values and we took them as 0 and 1, where step size as 0.1, and we took number of steps as 10. We're doing Euler method because it is the base method and it's the initial plot method which uses only single slope. Let's look at the MATLAB code for the RK2 method. This approach uses two slope estimates K1 and K2 to improve accuracy, where K1 is equals to h into f of x comma y and K2 is equal to h into f of x plus h comma y plus K1. Finally, we derive y value. This is better than the other one because it uses two values it accounts for both the initial slope and the slope after a full step. Next will be continued by my teammate.
Here, RK3 is also known as Ranson method, which builds upon RK2 by adding a third slope evaluation. The code calculates weighted averages of slope at different points in a step interval, resulting in higher accuracy. This makes RK3 more suitable for systems requiring moderate precision, though it's less common compared to RK4 due to the computational cost related to accuracy improvements. In the next slide, we'll see the MATLAB code for RK4. Finally, the classical RK4 offers the best balance of accuracy and efficiency. It uses 4 slope evaluation per step, averaging them with specific weights. The MATLAB code follows this process to deliver highly precise results. RK4 is a preferred method in many applications due to its reliability and ability to handle wide range of problems. Um, Coming to the graphs of RK1 and RK2, these demonstrate their respective accuracies. RK1 or US method shows broader approximations with noticeable errors over time. RK2 improves upon this by capturing mid-interval dynamics, providing a closer fit to the exact solution. These visualizations highlight the trade-off between computational simplicity and accuracy. And here, the graphs for RK3 and RK4 illustrate the increasing precision of higher order methods. RK3 shows a tighter approximation than RK2, but RK4 achieves near perfect alignment with the exact solution. These comparisons emphasize RK4's superiority in balancing computational effort and accuracy, making it a benchmark method for solving differential equations. Next slide will be continued by Maniti.
Okay, though using these RK methods, we have successfully modeled the population growth of fish species over a specified time frame. By adjusting parameters such as intrinsic growth rate and carrying capacity, we stimulated various scenarios, gaining a deeper understanding of their effects on fish population and their dynamics. Here, it also supports informed decision making to the ecologists, fisheries managers, and environmental scientists, providing a proper overview about habitat management and ultimately contributing to the sustainability of the fish population in natural ecosystems. Now I'm going to tell about some benefits of these methods. Here, the versatility of these RK methods can handle wide range of differential equations, including stiff and non-stiff systems. The accuracy, as the order increases, the accuracy is also increasing. The stability. RK methods provide more and wide range of step sizes and problem types. They can also adapt to the changing step sizes of time varying systems. Coming to the drawbacks of the RK methods. Here we can discuss some computational cost as a drawback, where higher order RK methods require more functional evaluations per step, leading to increased computational effort. Implementation complexity, where RK methods are relatively simple to implement, but higher order methods are complex. And also these are having the limited adaptability, which cannot adapt to the oscillatory or discontinuous systems. Also, these are not always preferred in every case. In some scenarios, the accuracy might vary in providing the efficient solutions. And we took the references of these papers. Thank you.